Alright, I guess let's begin the stream. Cool. Let's first go through the graph concepts, the basic graph concepts that we need. Alright. We have BFS of graph, DFS of a graph, and then bipartite graph, detect cycling graph using BFS, cycling graph using DFS, okay, directed graph, cool. Then we have Kahn's algorithm for topological sort, BFS, topological sort, DFS, and discuss the algorithm. All right, let's revise the concepts then. All right, we have some notes over here also, which is BFS of a graph can be used for shortest path problems as it checks first on the same level. Got it. DFS can be used for longest path problems. Got it. All right, let's do one thing. Let's see what all we have as a terminology. We have graph, of course, we have vertex, then edge, degree of vertex. Yeah. Number of edges that are incident to the vertex, which is in degree. Now degree, again, incident is that are incoming towards that vertex. Then we have path, cycle, directed graph, undirected graph, cool, weighted graph. All right. All right, connected graph. All right, then we have disconnected graphs. Great. All right, you get array list integer. This returns an array list of integer. That's BFS. You get vertex and you get edges. All right. Now what to do is create an adjacency list, of course. Adjacency list is nothing but a list of integer that is not add new and just integer. All right. Traverse for every single edge and all right, add that particular edge into the adjacency list. Got it. Basically, adjacency list is nothing but all the nodes that the current node is connected to. We keep a mapping of that, right? I got it. Great. Then we have a queue. Of course, we use a queue for BFS. Then डिस्कनेक्टेड कंपोनेंट्स के लिए है this one. Alright, we travel for every single edge and we check if it is, we keep a track whether we have visited it or not. Got it. Alright, basically why we are doing this for disconnected components is so that we don't leave any component unleft for traversal. So yeah, got it. Mark it as visited you true, offer q, right. Got it. This is the BFS basically. Then we have DFS with us. Adjacency list creation is something which will be same in every single graph problem, I guess. Right. Great. Next thing is what we do is create an answer. Alright, what do we do in this? Uh, uh, Alright. Mark current node as visited, then you do add it in the answer. Then you traverse every single node of the adjacency list. And if it is false, you traverse for it. Got it. That's how you do it. Great. What have I done here then? Alright, this is the traversal for a disconnected graph, which is, we're adding every single component over here. Got it. What we're doing here is passing this and component maybe I will be adding it, right? Yeah, got it. Color the nodes of graph with two colors. do this. Okay. You pass the color, right? Set the color. If color of adjacent node is -1. Check TFS, else if it is already equal to color, then return false. Got it. Yeah, makes sense. This makes sense. For BFS, it will be what? Make a queue offer the start of a node. Fill the color in first node, which is any color you prefer, then poll the node. Then you go on for adjacent nodes, right? Yeah. Then it's all about. Got it. Makes sense. Bipartite graph also makes sense. Alright, let's solve first problem then. What is it about? K9 cross N2T binary grid. Descriptions of map of ones and zeros. Return the number of islands. Number of islands, alright. Island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. You may assume all four edges of the grid are all surrounded by water. Got it. So we have something like a grid, a 2D array, which is what here? 4 times 1, then 0. Right. Then we have 1, 1, zeros, 1, 0, 1, 1, 0, 0, 0, 0. Alright, what's the number of islands we have here? Surrounded by water from all the four sides. One is this one. It's this one on the right. And if I go over here, it will be what? One island is this. These four ones. One is this. One is this. So there are three islands in this, right? Mm, got it. So this is one single island. Right. Okay, let me just open it in DL draw. What happened? Why is this not opening? Yeah, great. Here we go. Got it. So the island over here is, oh yeah, let's mark the island. Let me just zoom to 100%. This is the island, right? Yeah, this is the island over here. All right, this is one island. In second case, let's see the island over here. One is this, one is this, and one is this. Got it. So basically, these are kind of all the number of components, number of unique components of a graph, right? So for example, everywhere I receive a one, I add its adjacent node, and then what we do is we count the number of components. Basically, I list down all the adjacency list, and then I count the number of components in that graph, and that will be the number of islands that I have, right? Got it. So number of unique components basically. Alright, number of components of the graph or the number of islands. First step is we create an adjacency list. How do we do that? Let's do a list of integer. This will be new list, right? How do you create an adjacency list again? You get edges, yeah, for every single edge. Alright, so for every single edge, 0, 5, it is a 2D m cross n binary grid. So I got to create adjacency list first. Thing is, how do we create it? All right, let's just restart the timer once. Yeah, I think we can start the timer. That I know how much time I can solve this question. Started. I already have kind of an adjacency list, right? This is what an adjacency list is basically. I have one zeros, so I already have an adjacency list. It's like okay, I got to mark it as if it is one, then only we visit it, right? It's like pfs of grid and you pass u and v. Does this make sense? I do a dfs for every single component and then I increase the number of islands. Alright, makes sense. Private void tfs int v. Alright, now if the current point is either water or anything like that, I don't want to proceed further. So I need to check if it is a valid character or not. Like private return it from here. Otherwise, we need to mark it as visited, right? Yeah, we need to mark it as visited. There are two ways to do this. Number one way is keep track of all the visited elements using another visited array, but I have to specify we can't modify the input array. Nope, I guess we can do it something like this, like red u v. This marks as visited, right? Next thing we need to do is df plus v plus 1 and v. Does this work? Oh, it gave me what? Give me 9 islands over here and 7 over here. Alright, how is this possible? Alright, a second. I think this is the issue. Do it like this. This should work now. Okay, it still didn't work. Alright, the issue is we are checking for integer over here. However, this is a string. This should now work. Ideally, let's see. Yeah, it worked. Great. Clone graph. Given a reference of a node in connected undirected graph. Okay, basically every single node has its own neighbors thing also, which is kind of the adjacency list we need. What it does is, hey, wait a second. Every node has these neighbors, then simplicity each node will have the same value as the nodes index, one indexed, alright. There are no repeated edges and no self loops in the graph. All we have to do in this is create a new graph using alright. Basically, I just have to create a new graph from this, right? Alright. Cool. Basically, this will handle the case when the first node is either empty, either null, or has no neighbors. So yeah, there'll be 100 nodes. Okay. So it's like cloning the whole graph, right? So after this, what I have to do is create a new node clone, just like clone node.val, right? Then I have to create the whole graph as a clone. Got it? So what we do, we need to traverse every single node, right, to create this. So this is the new linked list. Okay, q dot offer. And the thing is, I can't simply just travel like this. Basically, I need kind of two queues. One will be for original node, one will be for cloned node. So instead of that, what I should do is store pair of both nodes. So it will be like this. It will be like new node, and alright, I need node and a clone. Right. Basically, I'm storing pairs of both original and clone nodes, and I do while not q dot is empty. Okay. While this is not empty, what you need to do is poll the current one. Then you have original node, and you have clone node. Adjacent node goes like this. Basically, it start traversing the neighbors of the adjacency list of this current node. Then what I do is this is current node value, and I create a new adjacent node. Okay. You have to also mark it as visited somehow. Create a new node. How do you plan to use visited? Not pretty sure actually. I go on current node. Then I go on, let's say, the next node, which is one के बाद it is 2, right? Then what do I have? It's 2, get the current value, it's 2. You create a new node, 2. Alright, what I'll do is right? Then you pass it as new adjacent and okay, this is false. Every single node will have a unique value. So if visited val is not true, what do you do? If it is not true, create a new node, add it, then add, so it will be done however, right? And the other thing is true. Oh, all right. R is top fill listed at -1. Oh, sorry, this is my bad. Do it with false. Great. No pointer exception cannot read field val because parameter 1 is null. See if this works. This should ideally, you must return a copy of all the nodes in the original graph. What? What? Original graph is empty graph, while copy graph contains nodes. Okay. It's like return null here, first of all. Right. What is happening? You must return a copy of all the nodes in the original graph. Why not returning a copy of all the nodes in the original graph? Node is null. Return null. The size is 0, return new node. You create a clone. New node with node.val. Yeah. Then what? create a queue with node and clone. Queue dot is empty. Node clone node. This will not return neighbors could be traverse. Int val adjacent dot val. Yeah. Then you create a new adjacent. Alright, every time we visit the node, we won't create a new node, right? If it's not visited, if it's already visited, then we don't create a new node. No? What if it'll be what? It's 7 clones, right? Yeah. So if this is not, this is null, that is it's not visited to this. Otherwise, this work. Alright, now this is val. Yeah, it worked. Alright, so what we've done here is basically these are the base cases. Next, what we've done is created a clone of current node, created a visited array for all the 100 nodes, initialize it with null, mark current value as the clone node. Then we keep a pair of node which is original and clone as a queue, right? Then until unless the queue is empty, we get original and clone, we traverse adjacency list of original, create a new adjacent node. If we have not already visited the node, then create a new node for that adjacent node and mark it in the visit array. Otherwise, just pick it from the already existing nodes list or the map and add it in the neighbors list. Yeah, cool. That makes sense. This makes sense. Alright, let me just great. Let's solve this problem. This will be the last problem of today, I guess. Yeah, this will be the last problem of today. What is it? There's a person triangular and the part is both Pacific and Atlantic Ocean. The Pacific Ocean touches the island's left and top edges. Atlantic Ocean touches the island's right and bottom edges. The island is a partition into a grid of square cells. You are given a m cross an integer matrix heights, where heights are represents height above sea level of the cell at coordinate RC. The island receives a lot of rain, and the rainwater can flow to neighboring cells directly north, south, east, and west. If the neighboring cell's height is less than or equal to current cell's height, Water can flow from any cell adjacent to an ocean into the ocean. Turn a to-do list of coordinates. Alright. Result I is equal to RICI. Notes that clean water can flow from cell to both Pacific and Atlantic oceans. Got it? It's kind of a weighted graph problem, first of all these are will become the adjacency list. What we have to do is got it. Alright, how we do this? I visit on the current cell. For every cell, I make a path to the heights lesser than the current cell's height. Right? And I keep on moving. So basically, over here, 0, 4, which is over here, it can flow into both. We're saying, okay. Then I have 1, 3, which is this. यहाँ से it can go to 0, 3. It's saying it can go to Pacific Ocean. Yeah, it can go to Atlantic Ocean also. Then we have 1, 4. 1, 4 it goes to 1, 3 first. Then it goes to 0, 3. Goes to Pacific Ocean. All right. So it's like you create a path. basically what is happening. Let's see. Let's just take a screenshot. Right. Let's see what's happening. We'll start from here, right? This will first create a business list. So wait. It is not directed, but weighted, right? So every single node will have its own weight. Okay, got it. What we need to do is, let's see. I'm here. All right. This is okay. I need to change the color. This is where I am starting, right? This is where I am starting, and let's say I send this to DFS. Okay, let's say I send this to okay, send to DFS algorithm. What my DFS algorithm will do, check if store previous node, then only move, right? So it's like you have a DFS algorithm also over here. It is private void DFS. Of course, you pass heights. Of course, you pass entire, and of course, you pass previous also. what we need to do is, okay, ये हो रहा है हमारे पास. Basically, if it is less than previous node, तभी it can go ahead, right? Yeah. If it is less than previous node, तभी it can go ahead. What if we check for every single row and column, right? It's like check for this, then check for this, then check for this, then check for this. Okay, same goes for these one, same goes for these, and same goes for these. We check if our border can actually throw water into the ocean. So it's like the swap. Okay, so basically condition swap because we start checking from the border itself. Now, if the border can actually, let's say, through the water, right? If this border can throw the water into this ocean, the market is true. Market is true. Check for both oceans separately, right? Yeah, we need to check for both oceans separately that if it can throw or not, if it can flow the water into it or not. So we need to create a map. Hence, create a mapping. Both oceans. Since we are doing it for every ocean, every single ocean one by one, we need to check for both the oceans, right? Yeah. Oh, great. That's the logic that we check. Now, how to check this is another question. Alright, since we're doing DFS, we'll start from the border, then we'll go upwards, right? For example, if in this case I check, if I start from 2 and go to this 4, okay, this 4 will also be marked as true for that ocean, and this 2 will also be marked as true for that ocean. Am I right? Yeah, actually, so यहाँ पे देखते हैं. What is it? What is this? 0 1 2 3 3 0 1 2 3 3. And take it, this can't flow the water into Pacific Ocean now. Let's say get one Pacific Ocean wala example 1 4 1 and 0 1 2 3 4. This is that, right? What it does is 4 4 3 2 2 throws, and this throws from here itself. Okay. It has only marked, has it marked on 3? Yep, it has. Has it marked 1 2? Because 1 2 cannot throw into that. Alright, got it. Got it, got it, got it. So basically any single point which throws water into both the oceans is how we are planning to do it. We also need to keep track of which ocean we are tracking for in this DFS solution. How do we do that is the question now. Let's see. We have intros. Then we'll of course have Pacific and Ocean relay mapping, which is Pacific. Why this mapping? Because we can simply mark any particular index as true or false in this mapping. So yeah, one thing we need over here is we need to pass this mapping also in the DFS so that it can mark whether it is true or false, right? Yeah, great. Now I need to start from the border itself. Because let's say, first of all, I go to height dot length. Yeah, let's say I go to rows first. What do we do in rows is the question now. First of all, we'll do DFS, that's for sure. DFS will be done twice, one for Pacific Ocean, one for Atlantic Ocean. And one I'll send Pacific and one I'll send Atlantic, this is for sure. What next? What next do we do? Heights will also be passed, that is for sure. Right. What next do we need to send? For rows, I need to send ith. For every row, I'll send 0 column, right? Which is I and 0. I'll send this as previous, and for every another row, which is what? This will be from 0 to rows, from here to here. right? I need to send from here to here also. So it will be I and value. This is something that will be done over here. Similarly for first of all, it will be 0, it will be calls, then it will be teacher.min value and specific for first rows -1 I and Atlantic. Alright, that's something we do. Then we need to write our DFS. Alright. First of all, the only direction are I guess you don't need to mark this as well, we just an extra thing. Basically I was marked. Alright, let's do it. 0 1 0 -1 1 0 and -1 0. These are the possible directions that are water can flow in, which is north, south, east, west. These are the directions. Next thing we need to do is we need to check for DFS, how to do this DFS actually. Alright, one thing over here is for int I rows specific Alright, this is what will be done, which is I'll add it into result if it is true for both Pacific and Atlantic Ocean. How do we check if it's true for Pacific and Atlantic Ocean is the question now. There should be base case, which is again if I is less than 0, j is less than 0, I is greater than or equal to ocean.length, j is greater than or equal to ocean0.length, or this can be simply called heights. Yeah, this is the base case of our DFS. Next thing is if I j is less than previous, or ocean of I and j is already true, do a return from here, which kind of also acts as our visited flag over here. Yeah, how do you mark ocean of ij as true now? how does it know if it's a Pacific Ocean or an Atlantic Ocean? For example, let's say I send it for Pacific Ocean from what 0 to 4. All right, let's say I send it from here. Goes down, and it goes here, it goes here, this goes here, this goes here. It's true. This goes here, it's true. Okay. Basically, yeah, यहाँ पे it'll go first. It'll go down. Yeah, then it'll go down again. Not exactly. It'll go to this side first. Yeah, it goes into Atlantic Ocean. It becomes true. Since it's already true, return every single time, and yeah, it will return here. Next is Pacific Ocean. For Pacific Ocean, what we'll do is again go to this side. Since it's an ocean, marked as true. As an every time I'm also increasing the I and J. Got it. So it goes from here. Marks as true. Let's say for Pacific Ocean first. Goes here. Marks itself as true. Alright, I think I gotta watch its video. I don't think I'm able to figure it out on my own. I think the basic logic is sorted, but the DFS thing I have to watch the solution first. Let's see.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve Pacific Atlantic water flow. So this is another problem from the blind 75 list, and that's why I'm doing it today. The link to the spreadsheet will be in the description again, and so we will be able to fill in one more graph problem today from that blind 75 list. We're nearly done with that list now. At least most of the important problems on this list. I think there are some binary questions that I haven't really done, and I might not do these because I feel like binary questions rarely come up in interviews. But for this problem, so the text is a little small, so let's focus more on the picture. So we're given a two-dimensional grid of values, and so each value represents a height. So this has a height of 4, this has a height of 5, etc., etc. We are claiming that the top border of our grid, everything right above our grid, and everything to the left of the grid is going to be called the Pacific Ocean, and everything to the right of the grid and everything below the grid is going to be the Atlantic Ocean. So for any particular cell, we want to know, can this cell reach the Pacific Ocean and can it reach the Atlantic Ocean? If it can, then we are going to include this position in the result. If it cannot reach the Atlantic and Pacific Ocean, then we don't include it in the result. So how do we know if this cell can reach the Pacific and Atlantic Ocean? Because clearly there's a path, straight to it. Well, there's one condition. We want to know if water from this cell can flow to the Pacific and to the Atlantic, and water can only flow from the perspective of a cell to an adjacent cell that has a value that is lower than the original cell or equal to the cell. And it can only flow in 4 directions, straight above, to the left, to the right, and below. That's pretty straightforward. Usually you can't go diagonally in these types of graph problems. And so in this case, for this 5, we see that the above neighbor 3 is less than 5, this is less than 5, this is less than 5, and this is less than 5. So clearly 5 can go to all of its neighbors. Now let's take a look at the 3. Okay, 3 has a neighbor 1. 1 is less than 3, so it can definitely flow in that direction. And now see, this 1 is bordering the Atlantic Ocean. So clearly that means 5 is able to reach the Atlantic Ocean. Now let's look left. It can reach 4, and 4 can definitely reach 2 because 2 is less than or equal to 4. So from this perspective, we can also now reach the Pacific Ocean. So water from this position can flow to the Pacific and it can flow to the Atlantic. So this position is going to be included in our result. So a brute force and naive way to solve this problem is to simply go to every single position, do some kind of graph traversal, DFS or BFS would probably work, and doing that search, check from a cell, can we reach the top and left border, and can we reach the right and bottom border? And if we can, then we're going to add this cell to the solution set. If we can't, then we don't add it, right? So if we're doing a DFS or BFS on every single position, starting at every single position in the grid, we're going to get a time complexity of basically the size of the grid. Let's say that's n times m, which is the dimensions of the grid. And if we do that from every single starting point, we're going to get n by m squared as the big O time complexity. And you might think, well, since we're doing this recursively, we're probably doing a lot of repeated work, right? So for example, if I'm starting at 3, right, doing a DFS from here, I'm going to go to its neighbors and then do DFS from here, 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 and here. And maybe, by doing that, I can cut out the repeated work, right? And so we won't have to, restart a DFS for every single position in the entire grid. And you might think that will work, but I'm pretty sure it doesn't. I'm not going to go through the details of why, and somebody in the comments can correct me if I'm wrong. Maybe there is a clever way to get that to work, but I tried to do it myself and I was not able to, so I don't know if it's actually possible to do it that way. There's a different clever way to solve this problem. How about something work? And you might think, right? And we're going to ask them all can flow to the Pacific and it can flow to the Atlantic. So this position is going to be included in our result. So a brute force and naive way to solve this problem is to simply go to every single position, do some kind of graph traversal, DFS or BFS would probably work, and doing that search, check from a cell, can we reach the top and left border, and can we reach the right and bottom border? And if we can, then we're going to add this cell to the solution set. If we can't, then we don't add it, right? So if we're doing a DFS or BFS on every single position, starting at every single position in the grid, we're going to get a time complexity of basically the size of the grid. Let's say that's n times m, which is, the dimensions of the grid. And if we do that from every single starting point, we're going to get n by m squared as the big O time complexity. And you might think, well, since we're doing this recursively, we're probably doing a lot of repeated work, right? So for example, if I'm starting at 3, right, doing a DFS from here, I'm going to go to its neighbors and then do DFS from here, 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 and here. And maybe, by doing that, I can cut out the repeated work, right? And so we won't have to, restart a DFS for every single position in the entire grid. And you might think that that will work, but I'm pretty sure it doesn't. I'm not going to go through the details of why, and somebody in the comments can correct me if I'm wrong. Maybe there is a clever way to get that to work, but I tried to do it myself and I was not able to, so I don't know if it's actually possible to do it that way. There's a different clever way to solve this problem. How about rather than us going through every single cell and checking if this cell can reach Pacific and reach Atlantic, how about we go start from the Pacific Ocean, right? And let's find every cell that borders the Pacific Ocean. Clearly, everything in the first row borders the Pacific Ocean, right? That means everything in this cell can reach the Pacific Ocean, and everything in the left column can also reach the Pacific Ocean. And starting from each of these nodes, what we're going to do is now find what are all the other nodes that can also reach the Pacific Ocean, right? So at the end, we would have, some kind of set, maybe, it looks something like this, right? Or whatever. And then we know, okay, these are all the ones in purple can reach the Pacific Ocean. And similarly, we would also do that with the Atlantic Ocean. We know everything here on the right side can reach the Atlantic Ocean. Everything at the bottom can reach the Atlantic Ocean. And similarly, we do some kind of graph traversal starting from each of these positions, right? And see, okay, what nodes can reach the Pacific Ocean as well. And at the end, we would want to go through every single position in the grid, and we'd want to find positions like this one that can reach the Atlantic and Pacific Ocean, that we marked as being able to reach the Atlantic and Pacific. And then from these ones that can reach both, we would add them to our result and then return the result. So that's kind of the general algorithm.
Wait a second. I've already... Oh, fuck it. Wait a second. I've already decided now what border can touch Atlantic. So I don't have to worry about how the DFS would do it, right? All I have to do now is that ocean I of j mark is true, and for every direction I'll do a DFS on the heights with I plus b of 0 and j plus b of 1. So I comma j and ocean. This should work now, I guess. Let's see if it works. Legal initializer for int. Oh, alright. How do I declare it? That's how you declare it, right? Is this not how you declare it? Int. Oh, alright. Wait a second. The issue is lying over here. Alright, it worked successfully, I guess. Yeah.
Of how we're going to do things. The reason this is more efficient, this is going to be big O n times m. We're not going to be revisiting nodes several times. We're not going to be rerunning a graph traversal. What we're going to be doing is starting at each of these nodes, right? Doing a depth first search, right? So for example, let's say we started at this one, right? We do a depth first search and then see all the other nodes that can reach the Pacific Ocean, right? Let's say we marked these and these, right? And then maybe we do the same thing starting at this one, right? And we'd go over here maybe, and then go over here, and then we'd come back here. If we ever got to a cell that we revisited, we would not want to continue our depth first search from a repeated cell, right? So we just wouldn't do that. So that's the main idea of this algorithm. But there's one last point I want to make before I start going through the code, and that is remember how if we're starting at a cell like this one, water can flow from this cell to a cell that has a smaller value, right? Like a small cell like 3, for example, and then it can flow down to a smaller cell like 1, and then it can reach the ocean, right? So if we are going starting from a cell and reaching the ocean, we are allowed to go at equal heights, so 1 can reach 1, or we can go in decreasing heights like these ones. But if we're going in the opposite direction, if we're starting at the Atlantic Ocean and going to a cell like 1, going to a cell like 3, and going to a cell like 5, then we're going to have to do the opposite. We can go to cells of equal heights or cells of increasing heights, right? You kind of see.
All right, let's see the brute force approach, which is backtracking. You get rows and calls. Yeah, analyst. Pacific is false. Atlantic is false. If Pacific and Atlantic. Let's dot add arrays dot as list. All right, got it. You do what is this and oh, got it. Yeah, this kind of is like the approach I used. Let's see the BFS approach of this. You create seam arrays. You get a Pacific queue, you get an Atlantic queue. Got it. So yeah, this question was solved successfully and correctly. Great, I guess yeah, that's it for today. Thanks for watching. We'll do the rest of Leetcode stuff tomorrow, I guess. And yeah, how much is left? Cool. We'll continue this tomorrow.